Hi, this is Dr. Penny Adversario for a most challenging learning session on sample size approximation. With the following learning objectives to be aware of the different factors to consider in the computation of the sample size, to know the elements that go into sample size computation, to distinguish the different formulas for sample size appropriate to one's study objectives, to compute for sample size using available methods, and to recognize strategies to minimize sample size. We start with generalizations on sample size. You have to compute the sample size as early as possible to be able to estimate the resources required and address the feasibility of the study. There are two sides to it. If you have an excessive sample size, it could just be a waste of resources, time, and money because an equally valid information could have been gleaned from a smaller number of subjects. If underestimated, an insufficient sample size has a low probability of detecting a statistically significant difference between groups, even if a difference really exists. Consequently, an investigator might wrongly conclude that groups do not differ when in fact they do. The formula for the computation depends on 1. The study objectives, whether estimating a mean or a proportion, or testing the hypothesis of a difference between groups on a mean or a proportion. For example, a study to determine the prevalence of e-cigarette use among adolescents will entail an estimation formula, while a study to determine differences in the prevalence of e-cigarette use among adolescents between public and private schools calls for a hypothesis testing formula. As to the type of variable, if it is quantitative, then it implies a mean value as the estimate. And if it is qualitative, it implies a proportion as the estimate. There is a difference in the computation of the sample size if a researcher wants to determine depression among call center agents using depression scores versus using level of depression as the proportion of those who are mildly or severely depressed as the outcome of interest. With reference to study design, generally, longitudinal study designs require larger samples than cross-sectional or case-control designs. In addition, the definition of the proportion in the formula will differ for association type of studies, meaning for cohort studies, it is the proportion who will develop the outcome in the unexposed and exposed group, while in case control, it is the proportion of those exposed in the disease group versus the non-disease group. Certain adjustments have to be made depending on the sampling. For stratified random sampling, when estimating for different units of analysis such as region or province, sample size has to be estimated for each unit or stratum. That is, a weight is incorporated into the computation taking into account the proportion of subjects in the stratum. With cluster, to address the limitation of lack of variability or homogeneity within clusters, the design effect or DEFF has to be adjusted. It is the factor by which a sample size for a cluster sample be increased in order to derive estimates with the same precision as a simple random sample. For most health surveys, a DEFF or design effect of 1.5 to 2 is acceptable. This means to obtain the same precision, twice as many would have to be studied as with an SRS strategy. That is, to achieve this, multiply the computed size by the design effect. And lastly, it is good practice to provide a correction factor for non-response or refusal rate in the estimation of the sample size, which is plus 10 to 20% from the estimated sample size. These are the steps in sample size computation. First, you need to resolve what the study objectives are. Are you estimating a mean or a proportion? or testing the difference between group means or group proportions, or determining an association between variables. Estimation objectives call for determining a numerical value, like for example, determining self-efficacy scores of students on online learning modality, or a categorical value, say the proportion of students who have high self-efficacy on online modality, while hypothesis testing objectives call for differences in self-efficacy scores between those on face-to-face versus online platforms, or associations such as determining factors associated with preference for online learning. By estimates, we mean the standard deviation of the mean, the proportion, the difference between means or proportion, the correlation coefficient, or a measure of association such as your odds ratio or your risk ratio. By convention, we set our alpha error to 0.05, which is the probability of rejecting the null hypothesis when it is true, and it is at most set to 5%. It is also equivalent to a confidence coefficient of 95%, which is how confident you want to be that you will detect a statistically significant magnitude of effect or difference. The level of precision is how large a difference from the true value can be detected, or how much error from the true value the investigator is willing to commit. If estimating a mean value, it is expressed in whole number units. If a proportion, by default, it can be between 3 to 5%. If with hypothesis testing, you need to set the power of the test, which is the probability that you will correctly conclude that a true difference or effect exists. Power is equivalent to 1 minus error, which is 0.80 or 80%. The inclusion of power of the test is only for hypothesis testing type of objective, and then you compute using the appropriate formula. This is the general formula for sample size computation. N is the minimum required number of samples. Z of alpha is the standard normal deviate corresponding to a set level of significance. If alpha is set at 0.05, the Z's of alpha is equivalent to 1.96. If with hypothesis testing, Z's of 1 minus beta is the standard normal deviate corresponding to the power of the test, and it is equivalent to 0.84. S is the standard deviation derived from previous studies if estimating a mean value. P is the proportion derived from previous studies if estimating a proportion. D is the maximum tolerable error deemed acceptable by the researcher, or also known as the desired precision. It is expressed in whole number units if estimating a mean, and between 3 to 5% if estimating a proportion. By estimates, we mean standard deviation, mean, proportion, difference between means, difference between proportions, correlation coefficient, and measures of association. Where do we get these estimates? From related literature or past studies, from the results of a pilot phase of a study, and from halfway through the study, and from expert opinion. S represents the standard deviation. If there is no standard deviation, it can be approximated using information on coefficient of variation as given in the formula, or deriving its values from confidence intervals or p-value. If not possible to estimate the proportion, use 0.5 since sample size is largest if p is equal to 0.5 and pq is equal to 0.25. This will give you a sample size of 384. If a range of proportions is given, get the value closest to 0.5. If there are many independent variables, use the important independent variable that has the greatest variance or standard deviation to calculate the sample size. This will give enough power for all the simultaneous variables. The methods for computing sample size are the following: manual computation through the use of formulas, tables of minimum sample size by Lemeshow, OpenEpi epidemiologic calculators, other statistical calculators like PyFace, your web-based calculator for computing sample size for correlation studies. Factors affecting sample size are 1. The desired precision. The higher the level of precision desired, from 0.05 to 0.03, the larger the sample size. The more heterogeneous the values of the parameter of interest, the larger the required sample size. Example, if the parameter of interest is household size, between a population whose number of children in the households is almost the same, compared to that of a population with differing number of children, the sample size of the former will be smaller. The higher the power, from 80 to 90%, the larger the sample size. The higher the confidence coefficient, as you go from 90 to 95 to 99%, the higher the sample size. This also translates to a more rigid criterion for significance, from 0.10 to 0.05 to 0.01. The larger will be the sample size requirement. These are the most common sample size computations: estimating a population mean, estimating a population proportion, hypothesis testing for the difference between population means, and hypothesis testing for the difference between population proportions. This is the formula for estimating a population mean. N is the sample size. Z's of alpha is the standard normal deviate corresponding to a set level of significance. By default, we set it at 1.96. S is the standard deviation derived from previous studies, and V is the level of precision that is desired, and it is in whole number units for estimating a population mean. As an example, sample size is to be computed on a study to determine the 6-minute walk distance among obese children in a selected private school. Your 6-minute walk distance is a submaximal exercise test that is used to assess aerobic capacity and endurance. The distance covered in meters over a time of 6 minutes. This is a source from the literature on the standard deviation, which is the estimate that is to be used for sample size computation. With the formula, Z is assigned a value of 1.96. S is the standard deviation, which is 65.5, derived from the previous study. And D is given a value of 10, which is 10 units away from the true value. Substituting the values into the formula for estimating a population mean, we get a value of 165 obese children. The second problem is estimating a population proportion. This is the formula. N is the sample size. Z of alpha is 1.96, corresponding to an alpha error of 0.05. P is the proportion derived from previous studies. Q is 1 minus P. V is the desired precision ranging from 0.03 to 0.05. As an example, sample size is to be computed on a study to determine the prevalence of diabetes mellitus among patients with tuberculosis enrolled in TB.'s outpatient clinics. A source from the literature provides this estimate: 18.4% as the proportion or percentage of TB patients diagnosed with diabetes. Using the formula with alpha set at 0.05, the Z deviate is 1.96. The desired precision is 0.05. The proportion derived from the previous study was 18.4% or 0.184, and Q is 1 minus P, so that is 1 minus 0.184, equivalent to 0.816. Plugging these values into the formula will give you 231 patients with pulmonary tuberculosis. Using tables of Lemeshoff specifically on estimating a population proportion with specified absolute precision and specifying a confidence level of 95%, you have here for your columns the proportion. Since 0.184 is nearer to 0.20, then we will use this particular column. Then D is the desired precision, which is 0.05. The intersection of the column 0.20 and the row, which is 0.05, gives us a sample size of 246. Using open source EpiInfo, on the left side, you have sample size. Under sample size, look for proportion. Clicking on proportions will open you to this window, which has default values which you need to change. The anticipated frequency is changed to 18.4% and the absolute precision is 5%. There is no need to change the population size if you do not know the size of the population where your sample will be coming from. Then you click Calculate. The results show a sample size of 231. We now go to hypothesis testing of the difference between population means. This is the formula for getting the sample size. N is the sample size. Z of alpha is the standard normal deviate corresponding to the set level of significance of 0.05, but this time it would also include the type of alternative hypothesis, whether it's one-tailed or two-tailed. Z of beta is now included because with hypothesis testing, you need to incorporate the power of the test, which could either be a z-value of 0.84 for 80% power or 1.28 for 90% power. These are the standard deviations of the two group means. These are the two group means. As an example, a researcher wishes to compare the mean systolic blood pressure of premenopausal OCP users with non-OCP users. A pilot study reveals that the mean systolic blood pressure of OCP users was 130 millimeters mercury with a standard deviation of 15, while it was 124 millimeters mercury with a standard deviation of 18 for non-OCP users. Determine the sample size needed to have an 80% power to detect a significant difference in the mean systolic blood pressure of the two groups at alpha equal to 0.01. The type of alternative hypothesis is two-tailed because the study just wants to detect a significant difference. So in the formula, Z of alpha corresponds to a value of 2.58 based on an alpha of 0.01 and a two-tailed type of alternative hypothesis. Z of beta is equivalent to 0.84 corresponding to an 80% power. S1 and S2 are the standard deviations of the two groups, and mean 1 and mean 2 of 130 and 124 are the mean systolic blood pressure of the two groups. So substituting these values into the formula, we derive a sample size of 178 subjects per group. Using EpiInfo, under sample size, go to mean difference. It will open you to this window and you have to change the default values. The confidence interval is 99%. You have a power of 80%. The mean systolic blood pressure for group 1 is 130 with a standard deviation of 15. And the mean systolic blood pressure for group 2 is 124 with a standard deviation of 18. The results show a sample size of 179 per group. We now go to hypothesis testing for the difference between population proportions. N is the sample size. Z of alpha is the standard normal deviate corresponding to a set level of significance and the type of alternative hypothesis, whether one-tailed or two-tailed. Z of beta is the standard normal deviate corresponding to the power of the test. P bar is the average of two proportions. Q bar is 1 minus P bar. P1 is the estimated proportion for the first group. P2 is the estimated proportion for the second group. Q1 is 1 minus P1, Q2 is 1 minus P2, and P1 minus P2 is the difference between the two group proportions. In this example, how large should the sample size be in each of the two groups of patients if the researcher wishes to detect a significant difference in the incidence of pruritus between two different doses of intrathecal morphine with a power of 80% at 5% level of significance? Results from a similar study in the literature provided the following findings. At 12 hours, 14% of those who were given 100 micrograms intrathecal morphine developed pruritus, and 33% of those given 150 micrograms developed pruritus. These estimates will be used by the researcher to compute for the sample size. So with 0.05 level of significance and two-tailed type of hypothesis, Z of alpha is 1.96. With 80% power, Z of beta is 0.84. Q1 is 1 minus P1, having a value of 0.86. Q2 is 1 minus P2 with a value of 0.67. P bar is the average of two proportions, giving a value of 0.235. Q bar is 1 minus P bar, giving a value of 0.765. P1 is 0.14 and P2 is 0.33. Substituting these values into the formula will give us a sample size of 77 patients per group. Using the tables of Lemeshow, specified as having a level of significance of 5%, power of 80%, and a two-sided test, the columns bear the x values, which is the lowest value or the smallest of your P1, Q1, P2, and Q2. The smallest of this is 0.14, and so the value nearest to 0.14 is 0.15. For the rows, it's the absolute difference between the two proportions, and the difference is 0.19, which is nearest to 0.20. So the intersection of 0.15 and 0.20 gives us a value of 73 samples per group. Using open source EpiInfo under sample size, you go to cohort/RCT. This opens you to a window on sample size for cross-sectional cohort and RCT with the following default values, which have to be changed. The confidence coefficient is 95%, power is 80%, the percent of unexposed with the outcome is 14% because 14% develop pruritus, which is the outcome, among the unexposed group, which is the low dose 100 micrograms morphine. The percent of exposed with the outcome is 33% because pruritus develop in 33% among those exposed to the higher dose of morphine, which is the exposed group. Results give a sample size of 78 to 87 per group. This example provides sample size computation for association studies with the objective of determining the association between dietary intake and recurrent respiratory tract infection in children. The journal provides an odds ratio of 2.988 on the association between processed food intake and recurrent respiratory tract infection in children. This estimate will be used in the computation of the sample size. Using open source EpiInfo, go to Unmatched Case Control under sample size. By inputting the value of 2.99 under odds ratio and clicking calculate, you get a sample size of 56 to 62 per group. In getting the sample size for correlation studies, we have the following example. What sample size is needed to be able to determine the correlation between length of screen time exposure and computer vision syndrome scores among first to third year medical students in the National Capital Region? A Pearson correlation coefficient of 0.248 from a previous study provided estimates for the sample size. Plugging this value into a web-based calculator for sample size computation for correlation gave 125 as the sample size requirement. To minimize the sample size, one can adjust the values of the elements that go into the computation by increasing the difference between group means or group proportions in the denominator, by using a one-tailed test of hypothesis, or by decreasing the confidence coefficient from 0.99 to 0.95 to 0.90. Use of continuous than discrete variables. This is to illustrate the differences in sample size requirement between using discrete variable, which is the proportion of RAID in sample size 1, and continuous variable, which are dental fear scores in sample size 2, on a study to determine the association between chronotype and dental fear. Use a more common versus rare outcome because the rarer the condition being investigated, the larger the sample size. Example, a study on coronary disease limited to those who are in the 35 to 55-year-old age group, since it is most common among the older age group. Also, reducing the number of treatment groups being compared. When the computed sample size is deemed too big relative to the population size, finite population correction can be applied using the formula. And lastly, when a study has more than one objective, the sample size requirements for each objective has to be computed, and the largest of all sample size computations is considered to account for all study objectives. In the textual description of the sample size approximation, indicate the estimate used, whether it's the mean with standard deviation, the proportion, the correlation coefficient, or a measure of association. The source, whether from literature, from the results of a preliminary or pilot study, or from expert opinion. The formula used, whether it's the estimation of a mean or a proportion, hypothesis testing for the difference between group means or group proportion, the level of significance, the power if the objective is hypothesis testing, and the desired precision if the objective is on estimation. This is an example of a textual description of a sample size approximation. You have the source, the proportions, the formula, the level of significance, the power of the test. These are my references, and thank you for listening.